My name is Anthony Semt, and this is Physics Lab 2, the motion of a falling object. In this lab, I'm going to be asking the question, how does the force of gravity and the drag force affect the motion of a falling object? I'll be using Tracker to analyze a video of a ping pong ball being dropped from rest. I'm then going to be creating two computational models, one that neglects drag force and the other that includes drag force. I'm going to compare these models and explain the differences and similarities in a hope to answer this question. So in this lab, I'm going to be using Newton's second law, or alternatively, the momentum principle, which states that the net force equals the change in momentum over the change in time, where net force is the sum of all of the forces acting on the ping pong ball. Drag force is a force that's in the opposite direction of velocity, or the F-gravity in this lab. So I'm going to be using two models, like I mentioned. Model 1, where I have F net equals Fg, and Model 2, where F net equals Fg plus F drag. So my procedures for this lab, I dropped a ping pong ball from approximately 1.3 meters, weighing 0.0027 kilograms. I then used Tracker to analyze the video, and then Excel and GlowScript to create the models and graphs. Here's my video. It's a short little clip just showing the setup of the lab. Then I went into GlowScript and analyzed my data. So as you can see in line 36, I have the mass of my ping pong ball. In line 39 and 40, I have the position and velocity vectors, respectively. They both were 0 to begin with. On line 44, I have my time step, which was the frame rate of my camera. Line 49, I have the gravity. Line 65, I have the end time, which was 0.633 seconds. In line 70, I have my F net, which in this model neglects drag, so that's not included. In line 74 and 76, I have the velocity and position update formulas, respectively. In this GlowScript file, I am including drag. So just about everything in here is the same, except for a few notable differences. In line 56, I have the magnitude of the drag force, which is B. I'll explain that on the next slide. I then have F net calculated a little bit differently. Lines 70 to 72 calculate F net, which includes F drag. As you can see, I have the magnitude of the velocity squared multiplied by the normal vector. Here are some models representing the forces acting on the ping pong ball in my two models. In model 1, on the left, I have no drag force, so only gravity. And on the second model on the right, I have drag force working against gravity. Here's a quick visual explanation of my two models. Of my three models, As you can see on the top here in blue, we have the observed data, then the no drag data right under that, and the drag data in gray. The model that is lower at the bottom is a model that happened faster. You can indicate that by selecting any given time, for example, any given position, for example, -0.5, and you can see that the gray model crossed that threshold first. So we're going to compare these models now. The relationship between the no drag model, the orange, and the observed data, the blue, was as one would expect. The no drag model took less time to hit the ground, and this indicates that some other force was working against gravity. In this case, I'm saying that that force is drag. So then in the drag model, what we saw was fairly unexpected. We saw that it was the fastest descent of the three. Now this may be due to inaccurate computational models or the result of some errors I'm going to discuss later on. So before I get to those errors, I'm going to analyze drag. Just give a brief explanation. Drag forces increase as the velocity increases until terminal velocity is reached. So what is terminal velocity? Well, terminal velocity is the speed when F net equals 0. In other words, the force of gravity and the force of drag are equivalent, so we're not speeding up or slowing down once we reach terminal velocity. The magnitude of drag, B, is based on the properties of the object, in my case the ping pong ball. So here are some possible improvements. My axis was at a -2.7 degree angle from the horizontal. This was to account for some movement in the ball. My hand may have caused some initial velocity, and the motion blur in the camera caused some errors in position data. I could have used a larger object over a greater height because the force of drag didn't have much time to take effect. Making these changes may result in a better model overall. So, in conclusion, the force of gravity moves opposite to the drag force until the two forces are equal. This is terminal velocity. I don't believe that we quite got there in this lab due to the limited time window of 0.633 seconds, but on a longer timescale, this will be seen. Additionally, drag force is going to increase as velocity increases, meaning the drag force is proportional to velocity. So, gravity and drag force on the falling object move opposite to each other until the point where they cancel one another out. Thank you. This is my presentation on the motion of a falling object, and I hope you learned something.